Welcome viewers to my channel. Today I am going to discuss the mechanics problem of previous Neet year. Okay. So our first problem is when a block of mass M is suspended by a long wire of length L, the length of the wire becomes capital L plus small l. The elastic potential energy stored in the extended wire. So now we have to calculate the elastic potential energy stored in the extended wire. So you have length L. When a mass is hanged by the string, this is capital L, its length becomes capital L plus small l. So we have to calculate the elastic potential energy stored in the extended wire. We know that the potential energy stored within the string, that is equal to work done. And what is work done? Work done is equal to average force into displacement. Displacement occurs small l. So average force is equal to 0 plus mg by 2 into small l. So the answer is mgl by 2. So the option is option 3. Okay. Our next problem is body A of mass 4m moving with speed u collides with another body B of mass 2m at rest. The collision is head on and elastic in nature. After the collision, the fraction of energy lost by the colliding body. So here you have a body of mass 4m moving with a velocity u. It collides with another mass of body B of mass 2m. It was initially at rest. So after collision, what is the so let after collision its velocity becomes v1 and its velocity becomes v2. Okay. So according to the conservation of linear momentum, as it is a elastic collision, we have initial total momentum m1 u1, that is u1 is equal to u plus 0 is equal to final momentum m2 v2 plus m1 v1. From here we can find out v2 equal to m1 into u1 minus v1 by m2. And according to the conservation of energy, that is according to the conservation of kinetic energy, we have half m1 u1 square is equal to half m2 v2 square plus half m1 v1 square. If we replace the value of v2 from the equation 1, we got v1 is equal to m1 minus m2 by m1 plus m2 into u1. Okay. So what is the lost in kinetic energy of the colliding body, that is of body A? So lost kinetic energy, that is equal to half m1 u1 square minus half m1 v1 square. So we have the value of v1 from here. If we put the value of v1, we got the answer. The lost in kinetic energy, that is delta Ke, is equal to 4 m1 m2 by m1 plus m2 whole square into half m1 u1 square. u1 means u given in the question. So now we have to calculate the lost in kinetic energy, the fraction of energy lost by the colliding body. So that is equal to delta ke by half m u square, that is equal to 4 m1 m2 by m1 plus m2 whole square. Here m1 is 4m and m2 is 2m. Okay, so by putting this value we got the answer, that is equal to 8 by 9. So this is the option 2. Our next problem is a body weighs 200 Newton on the surface of the earth. How much will it weight halfway down to the earth? Okay, so we have the expression for g dash equal to g into 1 minus d by r. So the weight of the body when it is halfway down to the earth is equal to mg into 1 minus r by 2 by r. So that is equal to mg by 2. So the answer becomes 100 Newton. The option is option 4. Our next problem is a solid cylinder of mass 2 kg and radius 4 cm rotating about its own axis at the rate 3 rpm. The torque required to stop after 2 pi revolution. So you have given the omega 1, that is the initial angular velocity, is equal to 3 rpm. 3 rpm, that is revolution per minute, that means 3 into 2 pi by 60 rad per second. So that is equal to pi by 10 rad per second, and it will stop so that its final angular velocity becomes 0 radian per second. Again we know that the work done W is equal to tau into theta. You have given that it will stop after 2 pi revolution. So theta is equal to 2 pi revolution, 2 pi into 2 pi, that is equal to 4 pi square, 4 pi square radian. 2 pi revolution, so number of revolution is 2 pi and a single revolution causes 2 pi radian. So that's why theta is equal to 4 pi square. Okay, so tau is equal to, again we know that tau theta is equal to work done is equal to half I omega square, that is the change in kinetic energy. Okay, that is omega 1 square minus omega 2 square. So tau theta is equal to half I. This is a solid cylinder, so moment of inertia of a solid cylinder about its own axis is equal to half m r square, and omega 1 square is equal to pi by 10 whole square. So again we have theta is equal to 4 pi square, so tau is equal to half into half. Here you have m is equal to mass of the cylinder 2 kg and radius is equal to 4 cm. So r square means 4 by 100 whole square into pi square by 100 divided by theta is equal to 4 pi square. If you calculate the value, it becomes 2 into 10 to the power minus 6 Newton meter. So option 1 is correct. Our next problem is a force F is equal to 20 plus 10y acts on a particle in y direction. F is in Newton and y given in meter. Work done by this force to move the particle from 0 to y is equal to 1 meter. So you have to calculate the work done. We know that work done is equal to dw is equal to f dot dr. So total work done W is equal to integral over F here dy, as the displacement occurs along the y direction. So F is equal to from 0 to 1, F is equal to 20 plus 10 y dy. So total work done becomes 25 joule. Okay. So the option is 3. Our next problem is the work done to raise a mass m from the surface of the earth to a height h, which is equal to the radius of the earth. So work done required to raise a mass from here, that is the radius of the earth, to a height h is equal to r. So what is the gravitational potential energy when it is at earth surface? That is equal to minus gmm by r. And when it is at a height, then the gravitational potential is equal to minus gmm by r plus h. So that is equal to minus So at a height is equal to minus gmm by 2r, gravitational potential energy at a height, when the height is equal to the radius of the earth. So the work done to move the object from earth surface to a height, that is the work done is equal to work energy theorem. We have work energy theorem, that is work done is equal to change in potential energy. So work done is equal to change in potential energy, U final minus U initial. So what is U final? U final, and we have U initial. So U final is equal to minus gmm by 2r minus this plus gmm by r. So this becomes gmm by 2r. gmm by 2r. Again we know that g into capital M is equal to g r square. So that is into small r by 2r to r. Okay. So the work done becomes small n g r by 2. So the option is 3. So option 3 is correct answer. Our next problem is a block of mass 10 kg is in contact against the inner wall of a hollow cylindrical drum of radius 1 meter, and the coefficient of friction is equal to 0.1. Minimum angular velocity needed for the cylinder to keep the block stationary when the cylinder is vertical and rotating about its own axis. So cylinder is vertical and rotating about its own axis. Let the block be stick here. Okay. So its weight acts vertically downward mg, and radius of the cylinder be r. So its centrifugal force acts m omega square r along this direction, and due to the normal reactional force acts inside. So the frictional force, so due to its weight, it will try to move vertically downward, and then its friction will act along vertically upward direction. So to be balanced, so F is equal to, must be equal to its weight. To stick on the wall of the inner wall of the cylinder, the frictional force must be equal to, must be or greater than equal to the weight of the block. So again we know that F is equal to mu into n, and here n is equal to m omega square r. So mu m omega square r. So mu m omega square r greater or equal to mg, or mu omega square r greater or equal to g. So the minimum angular velocity, for minimum angular velocity, mu omega square r equal to g. So omega is equal to root under g by mu r. That is the minimum angular velocity required to stick on the inner wall of the cylinder. So by putting its value, omega minimum is equal to 10 into 0.1 into 1, that is equal to 10 radian per second. Our next problem is the moment of a force given F is equal to 4 I cap plus 5 j cap minus 6 k cap at a point 2, 0, minus 3. About the point 2, minus 2, minus 2. So now we have to calculate the moment of a force, that is torque. Moment of a force means torque. Torque tau is equal to, you know, that R cross F. So here F acts on a point 2, 0, minus 3, and we have to find out the moment of a force about the point 2, minus 2, minus 2. So we have to calculate R first. Okay, so R is equal to 2 minus 2 I cap plus 0 minus minus 2, that means plus 2 j cap, and minus 3 minus minus 2, that means plus 2 k cap. So R becomes 2 j cap minus k cap. So it is torque. Tau is equal to R cross F, that is 2 j cap minus k cap cross F is equal to 4 I cap plus 5 j cap minus 6 k cap. So what is the result of the cross product? The result of the cross product becomes minus 7 I cap minus 4 j cap minus 8 k cap. Okay. Our next problem is a block of mass m is placed on a smooth inclined wedge ABC of inclination theta as shown in the figure. The wedge is given acceleration a towards the right. The relation between acceleration and the inclination angle for the block to remain stationary on the wedge. Okay, so you have given a wedge ABC here, that is ABC of inclined angle theta, and you have another block here. Okay, so its weight acts vertically downward, and that is normal direction force, that is theta. So the component of its weight is equal to mg cos theta, and along this direction mg sin theta, and an acceleration acts on the wedge, that is along this direction. Acceleration acts on the wedge. So a reaction acts on the block, that is MA, along the left direction. So the component of the reactional force MA, this is angle theta, so it is, so this is MA cos theta. The components of reactional force along this direction. So MA cos theta, to be balanced, MA cos theta must be equal to mg sin theta. So MA cos theta is equal to mg sin theta. So MA by mg is equal to tan theta. So A is equal to g tan theta. So option 2 is correct. Our next problem is a moving block of mass m collides with another stationary block of mass 4m. The lighter block come to rest after collision when the initial velocity of the lighter block v, then the value of the coefficient of restitution. Okay, so we have to calculate the value of the coefficient of restitution. So you have a block of mass m, it will collide with another block of mass 4m. Initially the 4m mass block was at rest. After the collision it becomes rest, and let after collision it becomes rest, and after collision it becomes velocity v2, and before collision its velocity was v and its velocity was 0. So that if we know that according to the conservation of linear momentum, that the initial linear momentum, that is equal to m into v, is equal to final linear momentum 4m into v2. Okay, so v2 is equal to 1 by 4 v. Now we have to calculate the coefficient of restitution. What is coefficient of restitution? Coefficient of restitution is equal to velocity of separation by velocity of approach. So velocity of separation means v2 minus v1, and approach, velocity of approach, u1 minus u2. Here v2 is equal to 1 by 4 v, v1 is 0 as it becomes rest, v1 is equal to 0, and u1 is equal to, here u1 is equal to v and u2 is equal to 0. So E is equal to 1 by 4, that is equal to 0.25. U is equal to 0.25. So the option 4 is correct. Our next problem is three object: A is a solid sphere, B is a thin circular disc, and C is a circular ring. Each have same mass and radius r. They all spin with same angular speed omega about their own symmetrical axis. The amount of work done required to bring them to rest would satisfy the relation. So which one relation will satisfy? So work done, we know that work done is equal to change in kinetic energy, that is half I omega square. Final kinetic energy, rotational kinetic energy becomes 0 as it stopped. So omega is proportional to I, as here the work done, this is work done is proportional to I, as omega is fixed. Again I for solid cylinder, we know that I for solid cylinder, that is the object A, is equal to 2 by 5 mr square. IB for the circular disc is equal to mr square by 2, and IC, that is for a circular ring, mr square. So we have IC has more value than the IB. So work done C is greater than work done B, greater than work done A. So option 1 is correct. Our next problem is a body initially at rest and sliding along a frictionless track from a height h as shown in the figure. Just complete a vertical circle of diameter AB is equal to D. The height is equal to. So you have a frictionless inclined plane which of diameter A B. The block initially is at here, is at rest, okay, is sliding from a height h. So whenever it reach the minimum point, the lowest point, its velocity becomes, that is according to the conservation of kinetic energy conservation, half m v square is equal to mgh. So v is equal to root 2 gh. So velocity at this point v is equal to root 2 gh, and diameter AB is the diameter. We know to complete a circular vertical circle, the minimum velocity required at the lowest point is equal to root 5 gr. So this v must be equal to the v minimum to just complete the vertical circle. So root 2 gr is equal to, root 2 gh is equal to root 5 gr. So 2h is equal to 5r, h is equal to 5 by 2 r, that is h is equal to 5 by 4 d, or d is the diameter. So the option 2 is correct. Our next problem is a solid sphere is in rolling motion. In rolling motion, it possesses a kinetic energy, that is translational kinetic energy and rotational kinetic energy simultaneously. The ratio of translational kinetic energy to the translational kinetic energy and summation of rotational kinetic energy. Okay, so you have to calculate kT by kT plus kr, that is the translational kinetic energy to the summation of translational kinetic energy and rotational kinetic energy. So we know that in rolling motion the translational kinetic energy kT is equal to half m v square and rotational kinetic energy kr is equal to half I omega square. As it is a solid sphere, so for solid sphere I is equal to 2 by 5 m r square, so half into 2 by 5 m r square into omega square. So that becomes omega, again we have omega is equal to v square by r, so 1 by 5 m r square into v square by r square, that is equal to 1 by 5 m v square. So kT is equal to half m v square by kT is equal to half m v square plus 1 by 5 m v square, 1 by 5 1 by 2 7 by 5 half 7 by 10. So it becomes 7 by 5. Okay, so the option 4 is correct.